So, welcome to this video, and in this video I'm really looking forward for this video because here I would like to talk about a very special question, and that's the question, how glides Batman? And therefore we have 3 points to discuss. So you learn how we make a model to solve this problem, so we need a scientific model to discuss this. And then we make a force balance in the two-dimensional case, which is related to the model I show you. And then you also see how we solve this balance by a Python script. So I'm a very big Batman fan, as you see also, sorry, here, right? There's a small Batman figure in my office. And if you take a look at these really cool movies, for example, here, we see how Batman jumps from the building and then he puts his cape and now he's gliding. And then he's frightening the people there a little bit, as you see, yeah, I think there. And then he's gliding, and then he reaches the villain, so he stops and starts to fight them. Okay, so, and the question behind, and the question I would like to ask is, can Batman glide as in the movie? And this is basically a hypothesis, right? We say, yes, Batman can glide as we see in the movie. And to answer this hypothesis, we need a model. And on the model, we can discuss this hypothesis. However, the problem is that Batman has a very complicated shape. So if we want to describe Batman, you can try, but it's not so easy. So my suggestion, or the suggestion here, is that we simplify it. And then we say Batman is a sphere. So sounds weird, but it's a very strong simplification. But the sphere has Batman's properties. So we have a sphere having Batman's properties, and with this sphere we investigate if Batman can glide. And what we also make to simplify is that we say Batman moves in 2 dimensions. So if you think Batman on the building jumps and then he glides, 2 dimensions are completely sufficient to describe his movement, right? And then we have to think, okay, which forces act on Batman when he jumps and glides? And now you can think about the previous videos, because we have a sphere in 2 dimensions and we apply a force balance on it, and this is perfectly particle technology, right? This is what we have in the videos before. And so what we have to, or how does the model finally look like? And this is Batman as a sphere, right, in 2 dimensions. So, and this, yeah, is something you should recognize. And if you think it's maybe a little bit weird, then you should look at the old videos. And then it looks again quite serious what we make in our model. And so if we again look at Batman jumping from the building, so this is downwards, this is getting distance, so plus in this direction, plus in this direction, so the velocity of Batman goes into this direction. There is a horizontal, or there's an angle theta to the horizontal, and then of course forces act on Batman, the same as for particles, right? So we have a gravity, something is pulling Batman down, or if it's a spherical particle, something is pulling the particle down. There is no difference here in this point of view. So gravity force, as you know, is mg, and then we have a drag force. So if Batman is moving in this direction, or the particle is moving in this direction, there is a drag force against it, and this is the density of the fluid divided by 2. Then we have the drag coefficient, which is a function of the Reynolds number. We have the area of Batman and velocity squared. This is the general drag equation. And now something new comes, and this is special for this case because Batman has this super cool cape for gliding, and therefore we have a lift force. And the lift force is something like a dynamic buoyancy. So, and the equation for the lift force is the same as for the drag force, with the only difference that we have CD for drag force, and here, sorry, it's not perfectly seen. So the lift force is density of the fluid divided by 2. The lift coefficient, and then it's the similar as here, it's the area of Batman times the velocity squared. Okay, and these are the forces acting on Batman. And what do we do now? If we have these force balance in a two-dimensional case, we have to split the forces into x and y direction. So there's a component in x direction, there's a component in y direction. So if we do this in x direction, we can take a look. So all forces summed up in x direction is the lift force and the drag force. The velocity is not a force, and the gravity only acts in y direction, so there's no component in x, so it's 0. So now we can take a look. So this is the drag force, and here we have the angle theta, and if we would look at this component, this is the cosinus, if the angle is here, to fd. So we have fd cosinus theta, direction minus, so minus. And here we have FL, and this is just turned on 90 degrees, right? So here's the angle, and then we have 90 degrees. So this is sinus of theta, and it points into the positive direction, so it's positive. And this is already for x direction and y direction. It's quite straightforward. So now we have the gravity, so Fg comes new, and gravity goes to 100% into y direction, so plus Fg, and we have minus Fl minus Fd because both act upwards in the y direction, right? And since this is sinus, this is cosinus, and since here we have cosinus, here we have sinus to get the other components. So now we already have the forces or the force balance in x direction and in y direction. And now we can take the very general equation F equals ma, and we rearrange this to a. And a is nothing than F divided by m. And we have an F description in x direction, which we can put in here, and in y direction, which we can put in here. So we have an acceleration in x direction, and we have an acceleration in y direction. So the acceleration in x direction is you put these equations here into these expressions, and then you divide by m and rearrange, and then you have the acceleration. This is a very good training for you. Try to do it. I don't do it step by step because of the length of the video, but you have to find a result. And what you need therefore is also this expression. So the velocity equals the square root of velocity x squared plus a velocity y squared. And the difference we see is that in x direction we have CL velocity y minus CD velocity x, and here we have CL velocity x plus CD velocity y, and we also have the g in here. So we have a positive acceleration in x and a positive acceleration in y direction, as we will acceleration, as we will see in a minute. Okay, so now we have two equations, and now we have to solve them. So how do we solve them? With a Python code. So therefore, as in the videos before, to start our Python code, we need to import libraries. We need NumPy for numerics, and we need matplotlib for plotting the results, because I would like to have a final nice diagram. And then we define a function, and this function is called acceleration. And this function has the equation acceleration in x and acceleration in y direction. So in this function we calculate these two equations. So we take the force balance, we set an equation for acceleration in x direction, for acceleration in y direction, and this function is then given into this into Python here, but Python also needs the information that the velocity is the square root squared x plus squared y direction, and we have the variables here. So the variables here is the velocity in x direction, velocity in y direction, the density, the area of Batman, the mass of Batman, Batman's drag coefficient, and Batman's lift coefficient. And with this we can calculate his acceleration in x and y direction. Okay, now we need to give all these parameters, and these parameters are assumptions. So the density of the air, and you will find, if you look really into DC universe, you will find the value of Batman's mass. And the area here was taken from the movie. So you can take the cape from Batman and measure the area of the cape. And now the important point is the cape, if these are similar like parachutes or something. And of course they have a different drag than lift. So these things are designed for gliding. So the lift coefficient should be much higher than the drag coefficient. And if we assume that Batman has something similar like a parachute, then we can take values known for these vehicles and tell, okay, Batman will probably, as the movie looks like, similar like a parachute, so could work in the same way. And he starts with 0 velocity because he's on the building just falling down, so there's no starting velocity. Okay, then we need a time interval. This is what we need always for our simulations, right? Time interval from 0 to 40 seconds in 1000 steps. And we have some starting values, so the values for velocity and position. There's a starting velocity which is set to 0, but you could also do the same calculation with a starting velocity already, but he starts at position 0x and 0y in the coordinate system. Okay, so now we need a loop, and the loop basically runs over the time interval, so from 0 to 40 seconds in 1000 steps. And dt is the difference between each time step. So we have a small time step, we calculate, small time step, calculate, and so on, and so on, and so on. And now what we calculate is the function acceleration. So we already defined the function acceleration, and now we calculate the function acceleration for a time step with the present velocity. And for the present velocity, which is at the beginning 0, we calculate the acceleration in x and y direction. And from the acceleration, we get a new velocity. And then the loop goes again and again and again and again till the time is over. So how does this work? So the new velocities are calculated by the so-called Euler method. And Euler method is nothing else than a numerical integration. So because if you integrate the acceleration, you get the velocity, right? So we have the old velocity plus the acceleration multiplied by the time interval, which is a numerical integration. So this is a velocity, so we can multiply it with this velocity, and this will give the new velocity. So we will have an increase in velocity at the beginning, and the same we do for y direction, and this is called the Euler method of integration, and this is what you see here. Okay, so here this is what the loop is doing after calculating x and y acceleration. So this is calculated by the function, and then we make this Euler method, and we're saving the new velocities. This is here, so we put the new velocities in the list. And then we also make the new positions. We calculate the new positions basically in the same way, because if we integrate the velocity, we get the position. And so this is what happens here, right? So again, Euler method. And then we only need to negative the y values, because y is directing downwards, not as regularly upwards. So we have to negative the values. And that's it already. So now we just need to plot the data, and therefore we have all these here in the plotting data. And when you plot the data, you to summarize the Python code, so we define the function acceleration, which is a result of our force balance. We set the parameter and the time interval, so all what we know about Batman and the air density and so on, and drag and lift, and these numbers you get from literature by make assumption as the parachute assumption. And then we define the time interval, which is needed for the Euler method. And then we have the loop, and the loop calculates the horizontal and vertical components of the velocity, and also the horizontal and vertical components of the position. And then we flip the values for the y values, and then we plot the results. And that's it. So finally, we will get these results. And what we see here is the velocity over time and the trajectory of Batman. And what we see here is the velocity. And you see he goes really, really fast. and then he's slowing down a little bit and fast, and then we reach a stable velocity about 22 meters per second, which is extremely fast. And especially if you think in the movie he's gliding, and the gliding looks quite good because here is Batman starting, and you see at the beginning he falls very fast, but then when the velocity homogenizes or sets to a fixed value, he's still gliding. So if the building is 200-meter high, we see he is able to glide, and here the number is around 550 meter. So at this position we have 550 meters, so Batman has a decent distance for gliding from a 200-meter building, but at the end of the video we see him very fast stopping and already start fighting. And this is not so easy if you have these super high velocities. So you can calculate the miles per hour or kilometer per hour from this, but it's really fast. So what can we say is Batman is able to glide based on our simple model, but he's too fast for these very direct stops. So he needs time to brake, right? To decrease his velocity. Okay, so the model I presented you is based on a paper from a group of students, and they published this already 14 years ago, but it's a very, very nice work which I use in my lectures, and therefore I would like to quote them, of course, because it's based on their work. And to sum up, so we set up a model regarding the question, can Batman glide? And the model makes some simplification where Batman is a sphere, and then we are very easy in particle technology, so we can make a force balance in the two-dimensional case and answer this question. And you see then, or you saw hopefully, how we solved this balance by a Python script, and the solution I showed you here in this video is a little bit different than the solution for the trajectory of the droplet. There was, right, in the previous video we discussed about a droplet and how far the droplet falls, which at the end is the same question because it's a sphere moving in two dimensions, but there are different assumptions which make them a little bit different in the details of the model, because the droplet we look doesn't have a lift force. But Batman has a lift force, and the Python scripts work a little bit different. In the previous model we didn't use acceleration. Here we use acceleration because I would like to show you different ways how to solve this question. And with this I hope you enjoyed the video and you learned something about Batman and particle technology. Thank you.